All right, it's 4 o'clock. Let's go and get started. Or good afternoon, everyone. How's everyone doing today? Excited for spring break, hopefully. All right, it's our last day before spring break, so thank you guys for coming. So I'm contractually obligated to be here, but I'm glad that you guys are here. I've talked to an empty room before. It's kind of a surreal experience, but it's definitely better to have people here and on Zoom, of course. So thank you guys for coming. Okay, so topic for today is we're going to finish up our lecture notes on Fourier series expansion. So this was a new idea that we started on Tuesday. We're going to finish up these lecture notes just because you're going to need it to do the homework, homework 5 that's posted right now. Okay. And then after that, we have spring break. And so I'm hoping to finish up everything today. And then when we come back from spring break, we'll start something else new. Okay. All right, any questions? I can answer anything before we get started. Okay, all right, let's go ahead and get rolling. Okay, so topic for today is Fourier series expansion. Okay. So basically the idea with the Fourier series expansion is that you can take any periodic function and represent them as a sum of sines and cosines. Okay. And so basically the idea with this is that sine and cosine, these are kind of our building blocks. So sine and cosine are naturally a periodic function, so they kind of repeat their pattern over and over again. Okay. And if you add up sine and cosine functions with different frequencies, right, then you can use that information and reproduce any periodic function. Okay. Okay, so basically it looks like this. And so we have f of t. Okay. F of t here, this represents any periodic function. Okay, so through a Fourier series expansion, we can represent it as this kind of infinite sum. So we have summation n is equal to 0 to infinity. Okay. So if you've never seen the symbol for this just means that we're going to add together everything that's in kind of its argument. Okay. We have an cosine of nt plus bn sine of nt. Okay. Okay. So quite a few things to kind of highlight in this expression here. Okay. First thing to highlight is that this is an infinite summation. Okay. And so in order to get exact equivalency, so in order for your periodic function to be represent exactly, you technically have to add together an infinite amount of terms. Which of course is not practical, right? Because nobody has time to add up an infinite amount of terms. That's why it's infinite. So literally no one has time to do that. And so we'll talk about some compromises that you can do for this today. Okay. So that's the first thing. The other thing to note is that these coefficients here, these a_n's and b_n's, these are the focus of a Fourier series expansion. So we call these the coefficients of our Fourier series expansion. Okay. And so in most problems where you're going to be computing this expansion, what that really means is that you're going to be computing these coefficients. Okay. So that's what we're going to be doing today. So, we did an example of that last time. So we did an example of computing these coefficients. So we're going to do more of that today. We're going to kind of gain some additional insights from there. So whenever you get a Fourier series problem, just know that you're going to be computing these coefficients here. Okay. And these coefficients, we have formulas for them. Okay. And so, for instance, we have A0. So A0 is the first coefficient of the A's, and we're going to talk about kind of what that means specifically. Okay. So this is equal to 1 over 2 pi integral from minus pi to pi of f of t dt. Okay. So that's how you get that first coefficient. Next one we have is an. So an here is 1 over pi integral from minus pi to pi f of t cosine of nt dt. So a little bit more complicated of an integral, and so you have to take the product of your periodic function and cosine over one period, okay? And then finally, we have the bn coefficients. So you have b sub n here is equal to 1 over pi integral from minus pi to pi f of t sine of nt dt. Okay, so get familiar with these formulas because these are the ones we're going to use to compute our coefficients. Okay, so that was just a review of kind of the theory behind this. And so, another thing I wanted to do today, and I don't want you guys to write this down again because, it's kind of a lengthy example. But I did want to just kind of talk through the example we did at the end of class last time because I think there's a lot of important stuff we can highlight from there. Okay? So we kind of come back up here. We look at the example. Okay. So you see we did a lot of calculations for this. Okay. So the one example that we did last time was we have this rectangular wave where our function kind of goes between these two values, minus k to k, and we want to compute the Fourier series coefficients for this periodic function. Okay. So you can see here that it's a square wave, it repeats itself, and so it kind of satisfies our criteria for a periodic function. Okay. And so what we did, we basically just went through all three of those formulas. We first computed a naught or a0. And so we plugged in f of t in here. We had to break apart the integral because it was a discontinuous function. Okay. And we got that a0 is equal to 0. Okay. Next, we computed an. So an, we did 1 over pi integral from minus pi to pi, f of t cosine nt dt. Okay. So we ran through that integration. And once again, we found out that an is equal to 0. And then we finally computed bn's, which was the first time we had a non-zero value, where we took the product of our function multiplied by sine nt, integrated from minus pi to pi. So we did all that, and we finally get a non-zero expression for bn, which is this. Okay. Now, after we got this expression for bn, we then evaluated these coefficients for various values of n. Right. So if you notice, this expression here depends on the value of n. Okay. Where n is going to count up from 1, 2, 3, and so on. Okay. So that's exactly what we did here. So for every value of n, we computed the value for bn. Okay. And we got all of these values here. So we got b1 is equal to 4k over pi, b2 is equal to 0, b3 is equal to 4k over 3 pi, b4 is equal to 0, and b5 is equal to 4k over 5 pi. Okay. Okay, so these are the first five terms in the expression. We could have continued. So technically, remember, our summation for Fourier series is an infinite summation, so we need to keep going. But we chose to stop at 5 just for our sanity. Okay. Okay. And so what we did from there was we plugged in those expressions into this infinite summation. And so we only plugged in the first 5 terms, and we got this function here. Okay. Okay. So plugging in the first 5 terms in this expansion, just noting that all of the a(n)s are equal to 0, we get, this f of t here, where we have 3 terms, where this term right here, this is the b1 term, this right here is the b3 term, and this term right here, this is the b5 term. Okay. And we're b2 and b4 in this case were equal to 0. Okay. Okay. And then the last thing I did before we left out was then, I took this function here, right? Even though it looks quite complicated, we could plot it in MATLAB. And what we can see is that our MATLAB code actually did a pretty good job kind of approximating this. And so the MATLAB code kind of did something like this. Okay. So it wasn't perfect, right? Because remember, we only did the first 5 terms in the expression, but our function actually did a pretty good job of approximating that curve. Okay. So this is the idea. So, you have your periodic functions in Fourier series. We want to find the values of the coefficients. And so if you did everything correctly, then if you plotted your function, you should be able to recreate your periodic function with those sines and cosines. Okay. Okay, so we're gonna do more of that today, but we're going to kind of build on this stuff, through our discussion. All right, any questions on just kind of the review from last time? Okay. Okay, so let's come back down here. Okay, before we do another example, let's talk a little bit about this infinite summation, right? So that's kind of the elephant in the room right now. Okay, so technically, you need to sum an infinite amount of terms for the Fourier series to be exact. Okay. Which practically is impossible. So nobody has the ability to sum an infinite amount of terms. Okay. So what we typically do, and just like we did in that last example, is we truncate the expression. And so we compute just a finite number of the terms, and we kind of truncate our expression with that amount. All right, so whether you truncate the expansion at 3 terms, 5 terms, 6 terms, 7 terms, usually in order for you to practically use the Fourier series, you just have to truncate. There's just kind of no other way to do it. Okay. And so this kind of has a couple side effects. Okay. And so the first one that's obvious is that it makes our problem practical. Right? We can't compute an infinite amount of terms. Maybe if we had an infinite amount of time, but life is finite here on Earth, and so you can spend the rest of your life computing an infinite Fourier series, and you would never complete because it's infinite. Right? The other consequence that you have here is that your Fourier series expansion is no longer going to be exact. Okay. And in fact, you saw that in the last one. And so in the last example that we did when we plotted it, right, we weren't able to capture that square wave or that rectangular wave perfectly. So we still had some oscillation, although, you know, we were starting to get there. We were starting to get kind of close, right? And so that's just kind of a trade-off that you have to do. So generally the relationship is that the more terms that you retain, so the more terms you have in your expansion, the more accurate your expansion is going to be. And so it's kind of a one-to-one kind of, you know, relationship between cost and benefit. And so if you're willing to kind of put in the work to compute 10 coefficients, 20 coefficients, 30 coefficients, then, you know, your result is always going to be more accurate. Okay. But you know, it's not a I would say a constant benefit curve where, you know, every coefficient gives you the same amount of benefit. Okay. For most functions, you know, most of the, I would say the accuracy comes from actually just the first few coefficients. Okay. And so usually once you get into the higher numbers of the coefficients, so n is equal to 10, n is equal to 20, you know, usually by that time, the coefficients are usually not that important. Okay. In fact, you know, let me illustrate this to you. So from the last example, okay, so we got our bn's equal to 2k over n pi times 1 minus 1 raised to the n. Okay. All right, and then we computed the first 5 coefficients here. So we did n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and n is equal to 5. Okay. Let's see what happens when we compute n is equal to 100. Okay. So this is a very, very high order coefficient term here. Okay. So that value here is going to be 2k over 100 pi times, well, 100 was a bad example because it's going to be 0 anyway, but let's do 101 just so we don't get 0. Okay. So it's going to be 101 on the denominator. I have 1 minus 1 raised to the 101 power. Okay. Okay, so if you look at this expression, right, and you compare to, you know, n is equal to 1, right? So our n is equal to 1 parameter is 2k over pi times 1 minus 1 to the first power. Okay. If you compare just the magnitudes of these two terms, you'll see that the n is equal to 1 parameter is a lot bigger than our n is equal to 101, right? And that's because, right, most coefficients will have this behavior where, you know, the magnitude or the value of the coefficient will start to decay at higher values of n. Okay. And that's usually going to be the case in most situations. So, That's one thing to kind of look for in your coefficients to say, you know, if n is in some kind of denominator term, or maybe it's in some kind of decaying exponential term. And so your coefficient should decay at higher values of n, okay? So if you truncate, you know, the last, you know, if you truncate everything past the fifth term, yes, you are throwing some information away, but most of the important information is kind of in those first few coefficients. Okay. Okay. Any questions on this so far? Okay, good. Okay, so now would be a good time to kind of have this discussion of, you know, why would we even do this in the first place, right? So why even go through the trouble of doing a Fourier series expansion? You know, it kind of just seems like a lot of work just for some, you know, just for some trivia. Because to compute these coefficients, you know, we have to do these integrals, which is, you know, kind of a lot of busy work. And in the end, you know, because of truncation, you know, we get something that doesn't even represent our original function to begin with. So it kind of just seems like a lot of work for just a lot of, you know, for really no benefit. Well, it's important from this perspective. So the Fourier series expansion is kind of the first of this idea of doing what's called frequency domain analysis. Okay. So in other words, you know, it lets us take a signal and break it down into each of the what are called the fundamental or the component frequencies. Okay. Okay. So the examples that we're going to do in the class, you know, don't really kind of do it justice because, you know, in class, you know, we're kind of limited just based on our kind of our human brains, and so we can't, you know, we have to kind of stick to ourselves with simple functions. But in reality, you know, you could have some very complex signals or very complex functions that you're going to be analyzing. Okay, and so one great example of this is the example that we started with on Tuesday, which is sound. Okay. So what we perceive as sound, right, is really just kind of a mix. It's a pressure wave, right? So we kind of established that on Tuesday. But you know, any given sound is, you know, pretty complex in that it contains a lot of different frequencies. Okay, even just the words that I'm kind of speaking from my mouth right now, it's not just one fixed frequency, right? And so it's because of, you know, how these frequencies are kind of manipulated, how I'm kind of changing the frequency of my voice based on, you know, my tongue and my throat and my vocal box and things like that. It's very complex. And so if you were to kind of measure the pressure waves coming in, you're going to see kind of a very, very complicated signal. Okay. Okay. So what you can do, so if you take, like, let's say you take a recording of my voice and then you, you know, and you want to break it up into its component frequencies, you can do that using the Fourier series expansion. Okay. And so through a Fourier series expansion or Fourier series kind of analysis, you can take any kind of complex sound or any kind of complex signal, and you can basically break it down in terms of seeing which frequencies are involved. Okay. And you can even go a step further. And so, not only can you see all the frequencies involved, you can see which are the most dominant frequencies within that signal. Okay. Because what do you get with Fourier series? So not only do you get the frequencies, you also get a coefficient that's associated with every single frequency in the signal. And the magnitude or the value of that coefficient will tell you how strong that frequency comes across, in that signal. Okay. So, if you were to take a recording of my voice and then, and then record it, do a Fourier series expansion, you'll see that, probably the most dominant frequency is fairly low. My voice is fairly deep for how small of a human I am. Versus, if you took a recording of my 12-year-old cousin, he has yet to hit puberty, and so his voice is going to have much higher frequencies than mine. Okay. So that's kind of the benefit, is that you can take each component frequency and see it all kind of laid out in a Fourier series expansion. Okay. You can do something cool as well. Kind of, right. So bringing this back to our idea of truncation, right? So if you're ever curious about how audio compression works, hopefully, I think you guys are all pretty tech savvy. So, there's a difference between, a very, fine concert that's recorded on like the best microphones that take up, gigabytes of space, versus kind of the janky recordings you took on your phone, right? There's a big difference in the quality of those sounds. Well, having a Fourier series analysis or Fourier, expansion will allow you to truncate certain sounds and compress them into, different file sizes. So that's why, even for the, the potatoes that you use to record, sounds in kind of a really, janky way, you're still able to make out most of the time, what people are saying, because, for the most part, those kind of low quality recorders, they truncate a lot of terms in the Fourier, but they're still able to capture the most dominant terms in the expansion. So you can still understand what people say. It's just not the most high quality, and there might be static in there and things like that. Versus, a very high quality microphone, very high quality kind of, computer that's recording these things, you're able to get everything that's said in very kind of crisp detail. And so the difference is, how many of these Fourier terms, what range of frequencies is recorded in these files. So if you ever get into this space, like audio recording, things like that, audio compression, you need to have kind of a strong understanding of how Fourier works. That's essentially kind of the backbone of that. Okay. All right. Any questions on this? Okay. All right. So let's expand our analysis here. So far, we've done an example of a Fourier series expansion with a fixed period. So the period was actually 2π. So you can do Fourier series expansions of any periodic function with any period, but you have to adjust your formula a little. So the above coefficient that we worked with last time and that we kind of reviewed today, that only works when the period of your function is 2 pi, which is very limited because there's a lot of functions out there that are not 2 pi. That you would want to take the Fourier series expansion, like a sound wave. Okay. And so in these situations, we have to adjust our formulas a little bit. Okay. And so for all these formulas, we're going to assume that our period has a value of 2 times L. Okay. So in other words, the value of L here, L is our half period. Okay. And so in this situation, our expansion would look like the following. So f of t is equal to summation n is equal to 0 to infinity an cosine of n pi t divided by L plus bn sine of n pi t over L. Okay. So you can see here that the argument inside the cosines and sines are adjusted based on our new period. And so instead of n times t, we have n pi t divided by L. Okay. So that factor inside there, the pi over L, that's just to convert between period of 2 pi to a period of 2 times L. Okay. And our coefficients change their values as well. So we have A0. Right. This is 1 over 2L integral from minus L to L of f of t dt. You have an is equal to 1 over L integral from minus L to L f of t cosine of n pi t divided by L dt. Okay. So you can see here all the sines and cosines are kind of adjusted to account for that change in period. Okay. So instead of just taking cosine of nt, we have cosine of n pi t over L. And then finally, we have the bn's as well. Oops. This is a typo up here. So in this expansion up here should be bn, not b2. But that. So I made this correction here. Okay, and then our bn's, our formula for that is 1 over L integral from minus L to L f of t sine of n pi t over L dt. Okay, so we're going to do an example after this for a function with an arbitrary period, and you're going to see how our process kind of modifies a little bit for these for this case. Okay. All right. Any questions on this so far? Okay. All right. So let's do an example to kind of see how this is how this goes here. Okay. Let's do this. Actually, let me do this example. Okay. So once again, we're going to have a discontinuous function, but we're going to assume it's periodic. Okay. So we're going to compute the Fourier series expansion. And we're going to do so for the following functions. So we have f of t is equal to. So it's going to have a value of 0 from t is equal from -2 to -1. Okay. It's going to have a value of we'll say 4 from -1 to 1. Okay. And it's going to go back down to a value of 0 from 1 to 2. Okay. Okay, so let's plot it out. Okay, so between -2 and -1, we're going to have a value of 0. So if we kind of plot those out here, we have -2 to -1. Our function is going to be 0. Okay. From -1 to 1, then our function is going to have a value of 4. So then it's suddenly going to jump up here, just like that. Okay. And then from 1 to 2, our function will go back down and have a value of 0. Okay. So once again, we have a square wave, we have a square pulse, except now it's kind of shifted a little bit and shifted up. Okay. And of course, this is a periodic function, and so it's going to just kind of repeat itself just like this. But that's the idea. So we have at least kind of one period of the function that we have, and we can compute the Fourier series expansion from this. Okay. Okay, so first thing we see here based on the function, the period of our function is 4. Right? And so it takes a time value of 4 in order for this function to repeat, right? So if I'm going from -2 to 2. And so that means our value for L, which is our half period, is going to be period divided by 2, which is 4. Okay, and so we're going to compute all 3 of the coefficients, so A0, AN, and BN. Okay. All right, any questions on the setup for the problem? Okay, all right, so let's go ahead and do our integrals here. Okay, so let's start with A0. Okay, so our formula for A0, we have 1 over 2L, integral from -L to L of f of t dt. So let's go ahead and plug the values in of our function for this one. Okay. So our value for L is 2, so we're going to have 1 over 4. And since our function is discontinuous, just like we did for the last problem, we're going to break up this integral into the 3 different zones. So we're going to have an integral from -2 to -1. Okay, so that's the first zone of our integral here. Okay. And so the value of the function in that interval is just 0 dt. Then we have integral from -1 to 1 of our second zone. And so the value of the function in that second zone is 4 dt plus integral in the last zone, which is integral from 1 to 2. Value of the function in that integral is 0. And so we have just like that. Okay, so let's go ahead and carry out these integrals. These are pretty straightforward. So our two integrals on 0, we're just going to cancel out because integral of 0 is just 0. Okay. And then for this function here in the middle, we have integral 4, which is 4t, evaluated from t is equal to -1 to 1. Okay. So this is equal to 8. Okay. So because we have 4 times 1 minus -1, which is 2. So 2 times 4 is 8. And then we divide that whole thing by 4. And so what we get in the end is A0 is equal to 2. Okay. Any questions on that? Yes.
Yeah, I was like, how did L become 2 again?
So L is the half period. So you have to look at the function that we have here and see kind of how long it takes to repeat. And so this function here has a period of 4. And so if you go from kind of where this function started at -2, and this function ends at 2, and so the length of that is 4. And so L is always the half period. So L in this case is L is 2. Yeah, definitely want to know it. And I think people get confused because people put L, they said L is the period, but remember L is the half period. So you take whatever period the function is and you divide it by 2. Yep. Any other questions on this? Okay. All right, so let's go ahead and keep going. So next coefficient that we have here is AN. Okay, so AN, let's go ahead and plug into the formula here. We have 1 over L, integral from minus L to L of f of t, cosine of n pi t over L dt. Okay. Okay, so if we plug into this here, we have 1 over 2, so that's going to be 1 over L. And we're once again going to integrate our function. So once again, we're going to break apart our integral into our 3 domains, okay? But I am going to just kind of skip a step here just because I know the first section from -1 to -2 is 0. The last section between 1 and 2 is also 0. And so my integral here is only going to be from -1 to 1 of 4 times cosine of n pi t over 2 dt. Where this interval here, -1 to 1, this is the only region where our function is non-zero. Okay. Okay, so let's go ahead and evaluate this integral here. So we have integral of 4 times that. So first thing I'm gonna do, let's take 4, let's take it out of the integral just so we don't have to worry about it. And so that's gonna be 2 integral from -1 to 1 of cosine n pi t over 2 dt. All right, let's go ahead and integrate this. And so we have 2 that kind of goes along for the ride. We integrate cosine of n pi t over 2 with respect to t. That's going to be equal to 2 over n pi sine of n pi t over 2. Okay. Evaluated from -1 to 1. Okay. All right, so let's go ahead and keep evaluating this. Okay. So remember, let's recall from last time that we have this kind of interesting trig identity where we said that sine is an odd function. And all that really means is that sine is symmetric across the origin. So that basically means that if you have sine of minus t, okay, this is equal to minus sine of t. So we can basically take the negative, any negatives that we have in the argument of sine, and then just take them out to the outside. Okay. So that's going to be relevant when we plug in the integration bounds here. Okay. All right. So when we have this, we have 4 over n pi. So I just took the two 2's and multiplied by each other. And then we have sine. And so we have sine of n pi over 2 minus sine of minus n pi over 2. Okay. So if we utilize that trig identity up there, and so we basically are going to take this negative that comes from the second term and just plop it out in front, okay? Which is great because then otherwise that term would cancel. And so if we do that, we get 8 over n pi of sine, or multiplied by sine of n pi over 2. And these are our ands. Okay. Any question on how we got that that expression for and right there? Okay. All right, let's before we compute the bn's, let's analyze this a bit, right? And so anytime you have sine of n pi over 2 or cosine n pi, remember n here is an integer, and so that can kind of help us simplify this. Okay, so this expression here is it's a little bit different than the ones we had last time, right? Because we have sine of n pi over 2. So let's look and see what value this will have at various values of n. Okay, so let's do the first 4, because usually after the first 4, you start to kind of get a pattern from this. Okay, so when n is equal to 1, we have sine of pi over 2. Sine of pi over 2 is equal to 1, right? Okay, now let's look at n is equal to 2. So when n is equal to 2, we'll have sine of pi, right? So we plug in n is equal to 2, so we have sine of 2 times pi divided by 2. The two 2's cancel out, and we just get sine of pi. We know sine of pi here is just 0. Okay. Okay, so for n is equal to 3, we have sine of 3 pi over 2. And so sine of 3 pi over 2, this is minus 1. And if we plug in n is equal to 4, we have sine of 2 pi, not 4 pi, excuse me. So we have sine of 2 pi, which is, again, 0. Okay? So what does this tell us? And so this tells us that for all even values of n, whenever n is an even number, then an is going to be equal to 0 because of this sine of n pi over 2. And then every other non-zero value for an is going to alternate between positive and negative. Okay. By the way, you don't have to kind of notice these trends, and so I've had students in the past that just said, I'm just not going to bother. I'm just going to plug in n when the time comes. That's fine. You can wait until the end, plug in n. But sometimes it's good to kind of notice these patterns, just to kind of give you some sanity check when you are computing the coefficients. But again, you can just plug in values of n at the end, and if that's how you want to do it, that's perfectly fine. You'll get the same answer. Okay. All right, so those are the ANs. So last one we have to compute here are the BNs. Okay, so BN, we have our formula is 1 over L, integral from minus L to L, f of t, sine of n pi t divided by L dt. Okay. Let's go ahead and plug in all of our functions and all of our values for L. And so that is 1 over 2. And once again, I'm just gonna do a little bit of a skip step here. So I'm just going to integrate over the non-zero portion of our function here. So integral from -1 to 1 of 4 times sine of n pi t divided by 2 dt. Okay, so same thing we did last time. Let's go ahead and evaluate this integral here. And so we have, if I bring out the 4, that's going to be 2. We perform the integral here. We have a minus 2 over n pi cosine of n pi t over 2. Okay. Evaluated from -1 to 1. And so let's plug in those integration bounds there. And so we have -4 over n pi multiplied by cosine of n pi over 2 minus cosine of minus n pi over 2. So same thing we did last time, except, instead of cosine, we started with sine. We integrate it. Instead of sine, we get cosine. Okay. Now, this one's interesting because, remember last time we simplified our expression because we said that sine is an odd function. Excuse me. Okay. Cosine is the opposite. Cosine is what we call an even function. Okay. So what that basically means is that if you have a negative argument within cosine, right? So let's say that you have cosine of minus t, right? Kind of the hallmark of the even function is that it is symmetric across the vertical axis, across the y-axis. Okay. So cosine of minus t is just the same thing as cosine of t. Okay. So the minus sign kind of just gets eliminated. Okay. And so because of that, what we can say is that this expression here, this cosine of minus n pi over 2, just becomes cosine of positive n pi over 2. And since we have cosine n pi over 2 minus cosine of n pi over 2, those two things, of course, are going to cancel out. Okay. And so what we get in the end is Bn is equal to 0 for all values of n. All right. So we have our A0, we have our A n, and we have our Bn's. Okay, any questions on this example here? Okay, all right, so now that we have our coefficients, we are ready to put it all together. All right, so we have f of t is equal to summation n is equal to 0 to infinity an cosine of n pi t over L plus bn sine of n pi t over L. Okay. So that's just our generic Fourier series expansion for a periodic function with a period other than 2 pi. Right? Every new chapter has a new mouthful of categories to say. Okay, so first thing we are going to do here is since we know for this problem that Bn is equal to 0 for all values of n, and so that basically lets us cancel out this entire term here. Okay. So we're not going to worry about the sign terms here because we know that all of their coefficients are 0. Okay. Okay, and so if we plug in everything else, and so we have f of t is equal to, first let's do a0. So a0 is going to be 2 right? So when n is equal to 0, cosine of n pi t over L just becomes 1, right? Because we have cosine of 0 there. And so that's why the A0 is kind of by itself. That's kind of why we compute separately as well. Okay. Next, we have the A1 term. So for the A1 term, we have 2k or 2 times, or excuse me, we have 8. My example in the notes here is k, but I plugged in k is equal to 4. So you have 8 over pi cosine of pi t divided by 2. Okay. So this term here is the A1 term. We know that A2 is equal to 0, right? So we kind of established earlier in this problem, for this particular problem, that for all even values of n, an is equal to 0. So we're going to skip A2 because A2 is going to be 0. Next one we're going to have is A3. But we need to remember that, A3, the sign is going to switch. And so it's going to go from +1 to -1. Okay. Okay, so for A3 here, we have a minus 8k, or 8, excuse me. Keep putting k there. So you have a minus 8 over 3 pi. Okay. Cosine of 3 pi t divided by 2. Okay. So this right here is the A3 term. And then let's do one more for good measure. And so the next non-zero one is going to be A5, because A4 is 0, remember. So we have 8 over 5 pi cosine of 5 pi t divided by 2. And this right here is the A5 term. Okay, and of course, this is an infinite summation, and so technically, we have to kind of continue this, but we only just computed the first, n is equal to 5 terms. All right, any questions on this example here? Okay, and so of course, you can go into MATLAB or you can go in your graphing calculator and graph this function, and what you're going to see is that it should, get you pretty close to this function here. Okay. Okay, so I don't think I'm going to get to half range expansions today, but I did want to cover kind of two kind of other things before we go. Okay, so first thing I want to talk about, which is perhaps a long time coming, is to kind of answer the question, why do we compute A0 separately from the other ANs and BNs? So let's talk about the role of the A0 coefficient. Okay. So A0 is actually a very interesting coefficient because it's the only coefficient in our expansion that's not multiplied by a sine or cosine. Okay. And it actually has a very specific meaning, within the context of this expansion. Okay. So A0, if you actually look at the formula for A0, so I'm just going to scroll up just so you can see it really quickly. Okay. Right. And so our A0 coefficient, we're basically taking the integral of the function by itself across one period and then dividing the whole thing by the length of that one period, right? So this formula, you've actually seen this formula before in your calculus course, or I hope you've seen this, okay? So this formula here is nothing more than just the mean value theorem. Okay? Meaning that, when you perform this calculation, so the integral of a function over a set interval divided by the interval, The result of that is going to give you the average value of that function within that interval, okay? And so that gives us some new life for kind of what the A0 coefficient represents. So the A0 coefficient, right? One way that you can see it is that it is nothing more than just the average value of our function across one period. Okay. So that's why it's most of the time it's computed separately from the expansion. Just because it kind of has that kind of special meaning, and you don't have to multiply by sine or cos. Okay. And so in fact, a lot of times when you see a Fourier series expansion, it actually takes the A0 coefficient and pulls it out. Okay. So a lot of times you'll see expressions that look like this. So f of t is equal to A0, right? So since it has kind of a special meaning, it's kind of off on its own. And then to this, you add the infinite summation. Okay. My summation things get more and more ugly every time. But if you're going to use this form, you're going to start the summation at n is equal to 1, right? So before this, we've started our summation n is equal to 0. Since we pulled out the A0 term, we can start our summation n is equal to 1 to infinity, an cosine of n pi t over L plus bn sine of n pi t divided by L. Okay, so sometimes you'll see this form. It's a little bit more straightforward, just so that you can see the A0, the ANs, and the BNs together. Okay, but that's why we have A0 set, because it represents the mean value or the average value of the function within R. Okay, any questions on this? Okay. All right, so last thing I wanted to cover today, before we head off for spring break, is let's go over this concept of even and odd functions again. Because if you can identify that your function is either even or odd, that actually can save you some work. Okay. And so if you look at the two examples that we did of Fourier series coefficients, they kind of fell within the same, there's a pattern that you guys might have picked up on at this time. Okay. So if we look at example 1, I'm not going to repeat example 1 here. Okay. Let me put this separate here. Okay. If you recall from example 1, we found that A0 was equal to 0, AN is equal to 0, but BN was non-zero. Okay. And if we look at example 2, the one that we just did just now, right? We found that A0 non-zero, right? So we got something that for A0, AN also non-zero, but BN was equal to 0 for all values of n. So that's not an accident. And so, in fact, there's a pattern that you could have picked up on from the original functions, which could have saved you some work, because for all of the 0 coefficients, right? If the coefficient is going to be 0 anyway, then there's really no point in computing it, because it's just going to be 0. And so if you're able to identify if your original function is even or odd, you kind of save yourself some trouble and just say that because this function is even, that tells me something about our coefficients for this problem. Okay, so the theory kind of goes like this. And so for even functions, or if your periodic function f And so if your periodic function f of t is an even function, okay? And then in those cases, a0 and an will be non-zero, but bn is guaranteed to be zero in these cases. And so in these cases, when you have an even function, so you know your input function f of t is even, then you don't even have to bother computing bn. You can just say that bn is going to be equal to 0. Okay. So let's look at our example that was even. So let's look at example 2. Okay. And from the picture, I'll show you kind of how it's an even function. Okay. So if you look at the graph for example 2 again, right? It looked like the following. So we had kind of the square pulse like this, and it even kind of continued on the x-axis just like that. Okay. Okay. So if you look at the graph of this function, and then if you consider the vertical axis here to be kind of like a mirror, right? What we can say is that this function is symmetric across this vertical line. So that means you're going to have the same value of the function on the left of that line as on the right, granted that we're an equal distance away. Okay. Mathematically, the way that this works is that if you have f of t, okay, right, the mirror image of this point is going to be f of minus t. So that's going to be on the other side of the vertical axis. And so for an even function, we have f of t is equal to f of minus t. Okay. And so when you're doing these problems, and so you're working on homework 5, and you can identify that your function is an even function, then don't even bother computing bn. Just kind of save yourself the trouble, save yourself the integration, and just conclude that this is an even function, and we can say that bn is equal. Okay. If you need convincing, of course you can still compute bn, but you should get 0 in those cases. Okay. So when we did example 2, we could have just said, okay, this is an even function. Let's just not compute bn's. All right. Any questions on this? Okay. And then of course the opposite is true as well for odd functions. So if your periodic function is odd, so if your input f of t is odd, and we'll kind of visually kind of see what that looks like in a second, okay? Then what you can conclude right away is that both a0 and an are going to be equal to 0. And so in those situations where you have an odd input function, don't even compute a0 an, because it's you're just going to end up with it being 0. Okay. Okay. And so let's draw out example 1, and I can kind of show you what an odd function looks like. Okay, so for example 1, we had this kind of square pulse again, but it was kind of modified. So I believe it looks something like this. And so we had function that looks like this, and then goes down, and looks like that. Okay. Of course, I'm only drawing kind of one period of this function, but of course it repeats. Okay. Okay, so what does it mean for a function to be odd? So mathematically, an odd function is one that if you take f of minus t, okay, so you kind of take the mirror image of f kind of on the opposite side of the vertical axis, what you're going to get is minus f of t. Okay. And so if you take any particular value here and you evaluate the same function on the other side of the vertical axis, right? So let's say we take the value right here, okay, right? So the mirror image of that point, so if you go on the other side of the vertical axis, you should get the same magnitude, but opposite in sign, right? And so if you go, that mirror image point is going to be right here, okay? So this first x here, this is going to be f of t. This second x here, this is going to be f of minus t, right? So same distance away from the origin, just on the opposite side. You can see that the sign of the function has flipped. Okay. Okay, and so if you have this kind of criteria, if you have this kind of behavior in your function, then you have an odd one, then you don't have to compute a0 or an. Okay. Another way that you can look at it is that if you draw a diagonal line like this, that diagonal line now becomes your line of symmetry here. And so just like we did in the even function, if you take a reflection of that point across that line, you should get the mirror image on the other side. This is a little bit harder to visualize because the symmetry line is slanted. But if you have good kind of spatial temporal awareness, and you can kind of flip things in your head with your head slanted, this might be a little bit easier. For me personally, this is a little bit hard for me to kind of visualize, and so I just go based on this test right here. Okay. But also, after you kind of see a few of these, you kind of see them quite a bit. You'll start to get some intuition in terms of what's an even function, what's an odd function. Okay. And if you compare this kind of methodology, you compare this kind of thing to sine and cosine, right? Sine is kind of the quintessential odd function, which correspondingly also corresponds to our Bn coefficients. Meanwhile, cosine is our quintessential even function. And so that corresponds to our An coefficients. And so this theory kind of aligns very closely to that. Okay. But before we end it today, I did want to make sure I went over this. So, when you're doing your homework, you can kind of save yourself some work. So most of the homework problems will be classified as either even function or odd functions. And so, use that to kind of save yourself some. Okay. All right. Any final questions before we wrap it up today? Okay. All right. And so thank you guys for coming today. Hope you guys all have a great spring break, and I will see you guys when you come back in about a couple of weeks. Have a good break, Professor. You too.